Good morning, everybody. Thank you for joining us today. Welcome to our webinar, Print to Perform, Digitally Accelerating Additive Manufacturing Using Simulation. Just to give you guys an introduction, this webinar will be about 40 to 45 minutes long, and at the end we're going to have a Q&A session. If you have any questions, at the bottom of the screen you can see a little Q&A section, so just type your questions over there, and we will try our best to answer all of them at the end. We also have a chat window, so if you have any trouble listening or any technical problems, just type it in the chat window and we will try our best to address those. I would like to introduce Arindam Chakraborty. He is the Vice President of Advanced Engineering at VIAS, and I will let him take over.
Good morning, everyone. This is Arindam here, and thank you for joining this webinar. I hope you will find it interesting, and maybe there will be certain problems that we can solve for you. Please feel free to ask all the questions that you have. If we don't have time now, we'll get back to you later after the webinar. This webinar most of the part will be presented by Rachel from Dassault System, and I'll just give you an introduction to our company and before we start the technical part of it. And so we are a Dassault System Simulia VAR. I'm just trying to forward the slide. Give me 1 second. So yeah, quick introduction to our company. So we are a Dassault System Simulia VAR. So we help customers with their licensing needs, and also we provide training and consulting services. We have been designated as a platinum partner for Dassault Systems. We do have multiple industry experience from our consulting side of things. So we have team members who have work experience in many different industries. Personally, I have worked in nuclear, a little bit of in medical devices, high tech, and oil and gas, and also some aerospace and defense work. Our main office is in Houston, but we also have presence in Chicago, Cincinnati, Fremont, California, and Portland, Oregon. We provide, apart from consultancy, we also provide training, and we do a lot of automation and customization services if you have a need. Our team consists of mostly PhDs and masters who have their work experience as well as their academic experience in design and manufacturing, solid mechanics, fatigue and fracture, thermal fluid. We have a good background in both CFD and FEA. We also provide data analytics services. We do sell all the Dassault System softwares, and as the part of today's topic, we also provide help with additive manufacturing, simulation, and 3D printing services. Some of our capabilities, as you can imagine, so we have a lot of capabilities around FEA, nonlinear FEA, complex material model, geometry, contact, and all. We have quite a bit of breadth and depth in fatigue and fracture analysis using FEA-based fracture and all. Polymer modeling, reliability and optimization is something we also provide as a service. We do a lot of root cause analysis and data analytics. Just to put into perspective a little bit brief history and the current status on AM simulation. So it's basically a process of joining materials, and this has been, I guess we can say this has been inspired by what is out there in the nature. So I have worked on some functionally graded material during my PhD work, and then it was a bio-inspired material because based on the loading requirement, we actually make a lattice structure. Our bone is basically a lattice structure which takes the load in the most efficient manner. So earlier the optimization were more limited by how you can manufacture it, but I think with additive manufacturing it's opening up to your imagination, and you can maximize your optimization algorithm to achieve a target performance. So that's where the additive manufacturing is coming in as a big change it's called as a disruptive technology as well. So we are looking forward to a great future with this manufacturing technique. I'll probably quickly go through the additive versus subtractive manufacturing. One of the thing is the material, so we can reduce the waste of the material, and another is with additive manufacturing, as I mentioned, it's about what you can optimize, how you can optimize your structure. That is becoming boundless right now. Of course, there are certain challenges, and simulation is there to help you, because that's how, if we can bring the physics inside your simulation model, then one can avoid doing a lot of tests and a lot of build with trial and error. And Dassault has a very good solution for that, which will be the topic of today's webinar that will start the technical part soon. There's a lot of standardization effort is going on, and like any other industry, eventually there has to be a strict standardization and all, but the Dassault system software is being developed as a more physics-based solution, and is to keep in touch with all the standardization efforts. So whatever the requirements are coming through standardization effort, so you should be able to see it reflected into the software capabilities. Also, one of the biggest tasks for additive manufacturing is verification and validation. Nothing in simulation can be used for with fidelity without the verification and validation part. So the software there is a lot of verification and validation effort going on to make this software robust and high fidelity solution. So if you have any question regarding like any reliability question or verification validation question with the software, we'll be more than happy to have a conversation with you. You can I'll mention that in the end as well. So we have our website and LinkedIn account, and you can reach us through phone and email. We'll share the information with you after the webinar as well. Having said that, I will request Rachel to start her part of the presentation. Thank you.
Okay, thank you. Can everybody hear me?
Yes, we can hear you,
Okay.
Rachel.
Okay, and you can see my screen?
Yes.
Okay, perfect. Thank you for the introduction. So my name is Rachel Fu, and I work with Dassault Systèmes with the Simulia brand, so a lot of kind of our simulation type of tools. So today I'm going to kind of go over the Dassault Systèmes capabilities, our end-to-end capabilities for covering additive manufacturing. And then, yeah, as was mentioned earlier, we'll have a Q&A session at the end. Yeah, so definitely bring your questions. Okay, so if we look at kind of an ideal world, we typically kind of look at the process of going from a raw metal powder to a ready-to-use part separately, and we really kind of designate challenges either, you know, to be design or how the part is actually going to perform in service. So design for additive is largely looking at things like kind of generative design tools, topology optimization, geometry reconstruction, and functional lattices. And then on the performance side, usually the challenges are more related to kind of accurately capturing loading and assessing things like, oh, is there going to be crack initiation? Is the part going to withstand its fatigue life? But when you start looking at additively manufactured parts, really the additive manufacturing process introduces a lot of factors that now kind of need to be considered when just moving from kind of your as designed part to your as manufactured part. So things like the support structures that are in your build, the tool path that you're using, these can really largely affect kind of your resulting part distortions, your residual stresses, and you know, your surface finish and your as-built properties of your manufactured part. So part of this is kind of understanding, part of understanding the material properties is really looking at during the build process, the microstructure evolution, grain growth, nucleation. So we really want to kind of use software here to help us understand this kind of process gap between our designed part and our manufactured part. So we really kind of need to connect all of these components. Okay, so the current landscape really for kind of software tools for additive manufacturing is really disjointed. So the designer, the manufacturing engineer, and the analyst are all really working on their own files, each with their own specialized software tools. And so the challenge has really become kind of managing all the data and translating this data between all these different software tools. So kind of the result of this disjointed environment is really that it can take, you know, weeks or months to kind of go from a design to get a successful functional part. So we're kind of trying to think of, okay, how can we get this down more to days, more on the scale of days to weeks? So instead of taking months to, you know, come up with a design and have it be a functional build, how can we do this on the order of days or weeks? So with Dassault Systèmes, so we kind of the next evolution of our software capabilities is all encompassed within this 3D experience platform. So the idea is that you know, Dassault has, you know, lots of different technologies available. So we have lots of different powerful CAD technologies, manufacturing technologies, simulation technologies. Can we bring this all to the same platform so that it can all use the same data, so that, you know, there is none of this time spent in translation? And so clearly for additive manufacturing, where one of the main issues is, you know, a disjointed landscape for software, the 3D experience platform is going to be a solution that is going to help address some of these AM challenges. So the 3D experience platform is really data driven. So again, all of the different capabilities within the platform are sharing the same kind of data set, but it's still model based. So your finite element analyst is still working on a model, you know, that is the same representation of data as the CAD designer, but everybody kind of does have their own specific model. So it's not too much of a paradigm shift that, you know, engineers will still understand the way these different models or these different roles work. What it really allows you to do is just stay connected with kind of all of the different engineering functions on the same set of data to help you kind of connect, okay, what's happening in the real world versus, you know, what you're virtually simulating or developing. So, you know, I mentioned before, so 3D experience, we're really bringing all of our Dassault technology and putting it into the same platform. So we're looking at kind of multi-scale physics, different ways of, you know, doing smart manufacturing and kind of having a lot of collaboration capabilities. But really all we're trying to do is allow engineers to be, you know, more efficient. So just kind of make you more efficient in the work that you're doing so that you're not kind of fighting with your software tools. So in terms of what kind of Dassault Systèmes is doing, like kind of from a bird's eye view for additive manufacturing. So this slide kind of shows the 5 different buckets or areas that we're focusing on for additive manufacturing. So the first bucket here is this 3D experience marketplace. And the idea of this, and this was kind of launched, I think, a couple months ago. So the idea is this is kind of an additive manufacturing community where people can collaborate on additive manufacturing transactions. So if you're a designer that needs to connect with print services, you can find, you know, different service bureaus here. Or if you're, you know, looking for some design services or simulation providers, this all happens in this kind of 3D experience marketplace. The second bucket is in silico material engineering. So this is kind of more this idea of doing molecular level simulations for doing materials development for additive manufacturing. So if you want to look at kind of different alloy compositions, things like that, there are simulation tools in this bucket that will help you with that. So this third piece here, this function-driven generative design, we'll go over this in this webinar. So this is this idea of you know, kind of design for AM type of tools for optimizing parts. The fourth bucket is process definition and production planning, and we will talk about this in detail in this webinar as well. So this bucket kind of encompasses setting up your manufacturing build, sending it to a printer, and then also using that information to do build process simulations, which is going to help you, you know, figure out if that build is going to be successful, so that you can kind of digitally work all of that out before you actually send any information to a printer. And then this fifth bucket is global production system. And so Dassault has capabilities for manufacturing and kind of monitoring your manufacturing floor. So these tools will help you, you know, make sure your additive manufacturing machines are all running optimally, you have enough materials, things like that. Just basically being able to manage your production system. Okay, so the first role or application I want to look at is this functional generative designer role. So the tools in this application are really kind of changing the paradigm from simply checking if your design meets requirements to using optimization tools to actually find the design that best meets the requirements. And because now with kind of advances in additive manufacturing, we can actually build these optimized organic designs. So the main advantage of this tool is really kind of the combination of a robust optimization solver, but it's coupled with powerful but really easy to use geometry reconstruction tools. So there's a simple workflow assistant that kind of guides the user through setting up the design space, loading conditions, and then your optimization targets and constraints. And then after your optimization is performed, you can kind of explore the optimized design space. And then kind of with a simple button click, you can actually generate CAD geometry from your optimized mesh. And then you can do your validation study on this geometry. So the other capability that this tool has is that different manufacturing constraints can be applied to the optimization. So we see here there are milling and casting constraints, versus say additive, where maybe you don't have any manufacturing constraints. So kind of these different manufacturing constraints, along with this variance creation tool that we have also in this application, really helps you kind of choose the best concept based on whatever your specific business key performance indicators are. So when you've gone through these exercises of these different optimizations, you've used the variance tools to decide on what your final concept is, then you can use our geometry reconstruction tools to kind of reconstruct high quality shapes, and that really kind of leverages the whole power of the CATIA modeling that we have within the 3D Experience platform. So when we talk to designers and manufacturing engineers who are looking at design for AM, we've really observed that the main pain point for generating this topology optimized geometry for additive is kind of connecting those optimized simulation results with a CAD geometry reconstruction. And so that is the process that can be handed off between a designer and a simulation expert, which can take months of work. But this role kind of really integrates that all into the same solution, so it can really save a lot of time in that space. So we've kind of seen how the interface looks, and so it's a very kind of intuitive designer-based interface to allow designers to have access to these simulation tools. But if we look at the technology kind of behind these tools, we can see that it's kind of based on our established Tosca and Abacus solver technologies. So topology optimization kind of gets increasingly more complex as you add nonlinearities in the model. So Tosca, which is a very advanced topology optimization tool, it really can cover all of these complexities up to kind of large relative motions, including friction. So currently our functional generative design tools include optimization with linearized contact, but our roadmap is to ultimately include all of these kind of levels of complexity. So we've also recently introduced geometry-based overhang constraints, and so this is specifically for additive. So this means you can kind of define your build direction, and it will include that in the optimization so that it can generate an optimized shape that is self-supporting or minimizes the amount of support structures required. So this final box here on the right is showing kind of the different levels of geometry reconstruction techniques that are available. So I mentioned earlier that there's a one-button click reconstruction tool, and that's this smooth surface method shown here. Direct modeling kind of lets you draw rough tubular shapes on a surface and then kind of merge those tubes and also use kind of dedicated drawing stripes. Or you can actually build in kind of parametrized shapes, so you can dimension different regions of the model. So you have lots of different flexibilities in how you're doing your geometry reconstruction. Okay, the next role I want to introduce you to is where we plan for the additive manufacturing build. So currently we support out-of-the-box powder bed fabrication process, and we have plans to expand to other AM processes, which I'll talk about in a future slide. So the first step here is what we call capturing the manufacturing environment with process reuse. And what this really means is that we can have a set of parameters that are specific to a given printer and material set, and then we ensure that these optimized parameters are kind of consistently used across an organization. The next step in here is process preparation, and this includes orienting the part properly on the build tray, generating support structures, and then nesting all of the parts that are going to be included in the build. So for part orientation, we have some geometric optimization tools, so you can do things like minimize supported area or minimize support structure volume. We can generate wire, tree, or volumetric support structures. And one important thing to note here is that these support structures are geometry-based, and this is unique in this space. So really, these support structure geometries can be used kind of upstream for design modifications, but they can also be used downstream for process simulations. So the nesting of the parts on the build tray we can do automatically according to some given rules or specified parameters. And then once all of your parts have been nested, the next step is to move to the slicing and scan paths. And those are generated based on process parameters, so things like laser power, hatch angle, scan speeds. And then once those tool paths have been generated, they can either kind of directly be sent to the printer via some virtual machine APIs or neutral file formats, or we can use them as inputs for process simulation. And so this is kind of the next piece that we'll see this for. Okay, so now we come to the additive manufacturing researcher role, and this is really where we're doing the process simulation or the virtual printing. And here we're really kind of using the data from the other two applications that we've discussed to do these process simulations. So again, this is already all built on the build setup that you generated in the previous application. So we're going to focus more in depth on this application for the remainder of this webinar. So within our process simulation application, we have a guided user interface for the powder bed process again. And this assistant really kind of walks you through the steps required to build a process simulation model. So because we're finding designers and manufacturing engineers are also interested in additive process simulation results, we really created this guided interface to contain the simulation best practices so that it's practical for non-simulation experts as well. So it's a simple to use interface, but underneath this, kind of graphical user interface is really kind of a powerful general purpose simulation framework. And this has been developed on our established Abacus solver technology. So the framework really kind of allows us to perform multiple levels of simulation within the tool. And we'll look at some details of that in the next slide, but really we're able to look at kind of detailed process level simulations, so looking at things like microstructure, or we can look at kind of what's more typically done, so part level simulations where you're looking at distortions and residual stresses for a given build part. But we can also look at build level simulations, so if you want to look at all the parts in the build tray and see if there are any thermal interactions that are occurring, we can do all three levels of simulation within the same framework. The framework is also configurable for different AM processes, so things like direct energy deposition, polymer extrusion, binder jetting, and we can cover kind of post-processing simulations, in-service performance validations, and things like looking at fatigue life, including those residual stresses and distortions from the build. Okay, so let's first take a look kind of at this AM simulation framework. So we've developed some new technology for the solver to be able to handle these additive manufacturing type simulations. And one of the kind of key tools in here is the mesh intersection module. So this is, one of the main and kind of very powerful features of the framework. So what this module does is it allows us to take process toolpath data. So that data is in the form of kind of time, XYZ, and whatever specific data set, say laser power. And it intersects this process data with any arbitrary mesh. So this means that we can use design as a starting point for simulation in that we can kind of directly mesh our CAD geometry. And we do not need to use voxel approaches. And this, is true regardless of kind of how complex the part is. So the solver is going to handle kind of sweeping through the finite element mesh with the toolpath and figuring out how to intersect that toolpath with the mesh to kind of accurately represent the physics of the build. So this process data can be directly obtained from print machines. So this could be at exact machine detail levels, and so that's, you know, millions of events, or you could use kind of a more lumped representation if you'd like. So really, the user kind of has control over the detail required in that toolpath data. So the toolpath itself can be assigned different geometric shapes for the mesh intersection calculation. So for example, for powder bed process, we kind of just represent the laser as a point and the recoater as an infinite line. And so as the laser is kind of passing through the part, you know, for a given element, for a given time increment, we're figuring out, okay, how many times does that laser pass through that element, computing an equivalent heat flux based on that. For a polymer extrusion process, you know, we may use something like a nozzle path represented as a rectangle as it's going and kind of depositing material. So these kind of different geometric shapes that we can assign to the tool lets us use this mesh tool intersection module to model lots of different types of additive processes kind of within the same framework. Okay, so this slide kind of talks to the additional technology strengths of the framework capabilities that we've developed that help you have accurate modeling of the physics for an additive manufacturing process. So as we talked about, the mesh intersection module lets you have any arbitrary mesh or time incrementation. So the user is really kind of controlling the fidelity of the solution with a mesh and time increment refinement. We also have built-in heat flux physics for handling multiple moving heat source types, so laser sources for powder bed processes, welding torch type distributions, or box lamp type heat sources. But you also have the freedom to kind of program your own heat distributions. We also have new capabilities for allowing elements to be activated in a progressive fashion during an analysis, and this is done in a computationally efficient manner. So during the simulation, any given element can be either kind of completely or partially filled with material or empty. And the solver is kind of keeping track of this evolution of material as the build is occurring. It's monitoring the mass, inventory, and distribution, and accounting for, you know, this addition of material during the printing. So finally, we also have partial facet areas that are computed, and this kind of allows us to have a precise assessment of cooling on the free surfaces of the part. And this is kind of regardless of the coarseness or fineness of your finite element discretization. So we have radiation and convection modeled on the free surface of the part as the build is occurring. And the solver is keeping track of all of that for you. Okay, so how do we do these process simulations? Whoops. So we perform the process simulations by doing sequential thermal stress analysis. So in the heat transfer analysis, the real, you know, scan data, or the real, say, laser path data is used to calculate the heat flux. And this gives us kind of a detailed temperature, it calculates the heat flux by including the detailed temperature dependent material properties and the build environment. So we have the build tray and the ambient conditions also accounted for. And this is going to give us, you know, kind of our resulting high accuracy thermal profiles for the build. We then use these thermal profiles to drive the stress analysis, and this is what is used to kind of compute structural deformations and stresses. So that's kind of the idea of how the overall simulation workflow looks. Let's kind of look now at the value that these process simulations can provide. So kind of working with different customers, we found that recoater interference is an issue, and this occurs when distortions cause the build part to rise up out of the powder bed. And this interference can kind of cause defects, porosity, or it can kind of completely kill the build. So to examine recoater interference, we can do a couple of things. So either we can monitor the distortions during the build on the current recoater plane, and we can check that these values are within a given tolerance, which is kind of what's shown in this animation here. we can also do the monitoring of those distortions during the simulation, and then we can terminate the simulation once, a failure tolerance is reached. So another reason that build failure occurs is due to high stresses that occur during the build, which may lead to kind of crack initiation and propagation. So because our process simulation tools are built upon our, kind of comprehensive abacus nonlinear FEM solver, we can also predict mesh-independent crack initiation and growth, based on a given failure criterion by using kind of existing XFEM technology. So we can put an XFEM enriched region on in a build model to look for crack initiation or growth during that build. So we can see that these process simulation technologies can be used to kind of predict different mechanisms of build failure so that you can virtually optimize your successful build before you go in and begin doing build iterations. Okay, so the real value in process simulations for additive really comes from, can we arrive at a successful build configuration without doing physical trial and error? But for this to actually be possible with simulation, our simulation runtimes really have to be significantly faster than our build times without a significant loss in accuracy of the results. So again, I mentioned our simulation framework allows the solution fidelity to be controlled through mesh size and time incrementation. So this means that we can kind of do trade-off studies to quantify kind of solution accuracy versus performance. And this is what this slide here shows. So we've kind of characterized the levels of solution fidelity as design through production to analysis, where design is kind of a fast solution, which is just required in kind of aiding design decisions, whereas analysis is a refined type of simulation where we have one build layer per time increment. So the chart on the left here shows kind of the time for a design level solution, and then the numbers on the chart are kind of a scaling factor on the design level solution for the other levels of fidelity. So if we look at this turbine blade, the design level simulation takes 33 minutes, production level simulation is about 4 times of that, and then the detailed simulation is 15 times of the 33 minutes, so say 7.5 hours. And then the actual build time is 35 times of this amount of time it would take you to do a design level simulation. So this kind of gives you an idea of, okay, how fast are the simulations compared to the build times? So clearly if we can do a design level simulation, this is going to be much more efficient than running the build repeatedly for different iterations. So this chart on the right here shows, okay, so if I can, do this design level simulation and it's faster than the build, what's my loss in accuracy of doing a fast simulation versus a very detailed simulation? So this really kind of shows the loss in accuracy in terms of peak distortions for these different levels of fidelity of simulation. So we can really kind of see that for the 3 parts studied, we can get a solution that's within 80% accuracy of a very refined simulation in under 2 hours, and this is kind of for even large parts with over 8,000 build layers, which is this hinge here at the bottom. So this just gives you an idea of, okay, you can control how fast you need the simulations to run by, increasing your mesh size, increasing your time increment size. And this gives you an idea of, okay, how much are the distortions changing when you do that coarser simulation versus a much more detailed simulation. Okay, so after the additive manufacturing build simulation, often you also need to simulate kind of the additional post-processing that's done to the part. So, it's not just built in its life cycle, it's going to go through a lot of post-processing treatments as well. So typically, wire EDM is going to be used to remove the part from the build plate. And then there's also going to be, heat treatment cycles or any other final kind of NC machining type processes. So we can use progressive element removal to kind of simulate wire EDM. And then we can also apply heat treatment thermal cycling to simulate that reduction of build stresses. And then, we can include kind of the distortions in that of the final build part, and we can include that in our NC machining code, and this can help you kind of with fixture design and your NC machining programming. Okay, so I mentioned earlier that one of the strengths of our solution is that the process simulations are really kind of built upon our comprehensive nonlinear finite element solver. So as a result of that, we are also able to do in-service loading of the additively manufactured part, because we can import the residual stress effects from the manufacturing history into our service loading simulation. So part failure and part durability are largely affected by these residual stresses from the manufacturing. So the ability to kind of incorporate them into our subsequent in-service loading type simulations is really important. Okay, so although kind of our out-of-the-box tools kind of currently support powder bed fabrication, the simulation framework is really highly configurable. So we've been able to use the same framework for different types of additive processes. So things like FDM, multi-jet fusion, or big area additive manufacturing, which is some work we've done with Oak Ridge. Okay, so far we've kind of reviewed 3 roles in our additive manufacturing solution. So we've looked at functional generative design, manufacturing planning, and process simulations. So the final role I want to show you is the reverse shape optimizer. And this is used for shape compensation. So this is really an established technology, but we're finding that the capabilities are providing a lot of value, specifically in the AM space. So effectively, all this tool does is really, it allows us to morph a CAD object by using point cloud data. So there's a couple of different ways we can use this. So we can, we have our process simulation distortion results. So we can morph our original CAD object based on those process simulation distortion results. And that gives us a CAD representation of, the predicted final build part. So we can do deviation analysis to kind of compare this with experimentally obtained measurements. The other kind of more interesting way we can use this tool is by negatively compensating the CAD part. So, we have these predicted build distortions. We can compensate the CAD part based on a negative scaling of those distortions. So then when you actually build that negatively compensated part, as it distorts during the build, it actually gets closer to your as designed geometry instead of further away. So because again, this is a nonlinear process, you may have to do this iteration loop a couple of times, but we have this set of tools that allows you to do that. And so you can actually kind of virtually work out a geometry that when printed will result in your kind of as designed part. So you don't need to do build iterations to see what those distortions are. You can do all of that through simulation and compensation. Okay, so next we kind of move into materials coverage. So Dassault has solutions to kind of cover multi-scale material modeling, and this is important especially for additive manufacturing because that, all scales happen during additive manufacturing. So before the print, we have phase field simulations, and this is where the user can kind of study the effect of various alloy additive content on the phase transformation and grain morphology. So you can look at kind of different temperature gradients and different cooling rates and see what the resulting phase transformations are. And you could do this for a variety of materials. And so Dassault again has tools within our Biovia brand for doing these types of simulations. So if we look in the middle box, during the print, we have solutions to capture material property evolution. So we can monitor the cooling rates in these thermal analyses for our build process. And by monitoring those cooling rates, we can really predict the metallurgic transformations that are going to occur, which will give us, phase content, grain nucleation, and porosity. And then once we have kind of these microstructure results, we can then translate that to, as-built macroscale material properties of the part. And then after the print, when we're looking more at material performance, the users can really kind of map you know, as I mentioned before, those process-induced residual stresses and strains into any in-service performance simulation. And then, you know, because this is built on our, you know, Abacus solver technology, you have access to kind of the full library of complex Abacus material models and contact damage and various kind of downscaling and upscaling techniques. Okay, so, you know, we have all of these nice tools, and then the question is always, okay, is it really predictive, this simulation capabilities? So we've done a lot of validation efforts looking at temperatures, distortions, residual stresses, and microstructure for a lot of different processes and materials. So we kind of start with coupon level deformations, and so here we can show that, you know, we worked with Renishaw on using different scan patterns and matching distortions for these kind of simple bridge geometries. And then we can also kind of just use material properties from literature to blindly match you know, various experimental results. And this is because it's a full thermomechanical solution. So we don't need any calibration. We can use, you know, typical material properties to match experimental results. And then we've done some kind of slightly more complex geometry distortion result comparisons. So after we've looked at kind of this coupon level or simple level of deformations, we move to build part level deformations. And so this box here on the right is kind of showing the work we've done with Oak Ridge and their big area additive manufacturing, where we start with doing a kind of a thin walled structure to look at, you know, predicted distortions, make sure we have the right heat transfer coefficients, things like that. And then we can move to looking at things like this full-size backhoe, which, you know, takes a week to build and 6 hours to simulate. So there's kind of some clear value there in having validated simulation capabilities. So we're also kind of the first process simulation software to validate residual stresses that are induced by the AM process. And so we've compared this with some experimental residual stress results reported in literature for this L-shaped column for stainless steel. And then we've also shown that we can look at microstructure predictions. So melt pool evolution predictions, we've been able to look at melt pool size and overlap due to interaction between laser beam and unfused powder. And we, again, compared that with experimental results in literature. And then we also have validated kind of location-specific microstructural features, such as grain size, morphology, characteristics, and phase fractions for titanium. And this was done with TWI. And so we were able to accurately kind of predict phase contents compared with what, you know, TWI found in experiments for titanium 64. And then we also found that we could predict porosity from unfused regions kind of along the boundaries of these columns that they were investigating. And so that validation work was done and is available also to share. So really kind of our validation efforts, you know, we have done a lot of validation efforts on a lot of different processes. So, you know, SLM, LDD, FDM, MJF. We've looked at physics, you know, starting with the basics from just temperatures all the way through to microstructure. And we have a lot of validation exercises for various materials. And so, you know, these are all kind of compiled here, and we can share this as necessary. So, you know, just let us know if something is of interest. And then kind of what do we do now with that we have validated process simulation? Well, you know, we can move towards things like process parameter analytics, where we, you know, want to tweak our process parameters to, say, minimize distortions. We can do that with validated simulations. And one of the other goals, I think, in the industry is also this process parameter mapping. So, you know, we can use simulation to figure out, okay, for this set of process parameters, you know, what do we expect the resulting part to be, so that, you know, you're not running simulations every time. You just kind of have a map that shows you, okay, what your parameters should kind of look like for, you know, a given material set and printer. And then the other way we can use validated simulations is now looking at things like optimizing support structures. So, you know, because we have this integrated workflow of support structure generation right through to simulation, it's really easy to vary those support structures and see, okay, what is going to minimize distortions, be best for heat transfer, things like that. And then we also have various infill density optimization workflows and lattice sizing optimization workflows. So again, if any of these are of interest, we can kind of discuss them in more detail. So the 3D experience platform, it has a lot of different tools for collaboration, for file management, and this is where all of these applications that we've discussed reside. And so we're really kind of working on our on bringing all of these tools together in the additive space on the 3D experience platform. So the 3D experience platform is available on-premise and on cloud. So obviously the advantage of on cloud is that there's no resource hardware investment required. We also have some kind of flexible burst licensing, which can be useful if your simulation workload is really variable. But on-premise is also available if you need to kind of keep the data siloed. Okay, so really we've talked about the landscape is very disjointed for additive manufacturing software. So Dassault's strategy is this kind of end-to-end digital manufacturing because we really have a lot of this technology. We have topology optimization solvers, we have fracture and failure capabilities, we have shape morphing tools, we have virtual machines. So we really just kind of need to put all of that technology together into these different applications which I've described. And this, everything is within the same data set. And so this kind of helps, engineers not having to translate data. So kind of our goal is within this unified platform, it's going to take you much less time. So maybe on the order of days to weeks in order to get from kind of a design to a part that's working in the field. So, so all the material that I've presented today is kind of our, I guess our 2017 version of the software. So we have some updates that have recently become available in 2018. And we actually have an upcoming Simulia e-seminar on May 17th talking about kind of the enhancements to the different tools that I have just explained in this webinar. So we have some advancements in our functional generative design, so things like we can do assembly level optimization. We have some new manufacturing constraints, some new thermal conditions that can be applied. We will have some new additive manufacturing planning roles. So we'll have a powder bed programmer role, which will include some simulation capabilities kind of built into the manufacturing planning. And then we also have roles for direct energy deposition and material extrusion coming. And then on the simulation side, we will have an eigenstrain method that's new, and we'll look at how that can be used for different kind of support optimizations. And then we also have some new heat treatment work to show. So if you're kind of interested in seeing, okay, what's new this year, based upon the tools I've explained, please kind of keep your eye on this link, and this is where this e-seminar is going to get posted. So the other kind of good place to get information here is, so we'll have our Science in the Age of Experience conference, and this is going to be June 18th to the 21st in Boston. And as part of kind of our, this is like our Simulia Biovia Geovia user conference, but we will also have an additive manufacturing symposium as part of this on June 18th. So additive manufacturing symposium is really kind of where you can come talk with other kind of people in the industry about, how can this DS technology help, your company kind of optimize in its own, additive manufacturing strategy. So we've got topics kind of broken up from, design for AM through process simulations, also looking at material design, and also kind of looking at the biomedical industry, how 3D printing fits in there. We've got keynotes set up already, so Airbus and University of Denmark, they'll be presenting keynotes. And then we have a lot of different papers that are presenting, showing a lot of these kind of validation type exercises, how simulation has been useful in these different kind of organizations and where they hope to go with these technologies and these tools. So as part of the Additive Manufacturing Symposium, we also have a free hackathon event. And so at this event, we have all of these tools that I've showed you available for people to try, and we'll have kind of some quick start lectures. We have some engineering challenges set out, and we'll have kind of teams of engineering students who are going to come and kind of compete on these different challenges for pretty substantial prize money. It's also really great for professionals to, come and try out the tools, talk to, kind of some expert application engineers on these tools that we've been discussing here. And so to register for this, please go to this link, and you'll see registration for the symposium and the hackathon and the entire Science in the Age of Experience conference. Okay, so that kind of concludes my presentation. We still have about 8 minutes for questions, so if there are any questions, please let me know.
Thank you, Rachel. That was a great presentation. So we are taking questions now, and I think we have a question already.
Okay. The question in the chat panel is, how and what do you provide in the quality report along with the processes? I think this might be related to what was presented in the previous presentation. Is that correct? Okay, well, we might have to get back to that. I think that might be related. Oh, go ahead.
Yeah, this is Arindam here. Sorry, I was on mute. And thank you, Rachel, for the nice presentation. It was very useful. So I think in terms of quality report, there will be. So if you have a benchmarking problem, of course, it will show you. You can set it up as an output for certain parameters, and if you have some physical data to validate, it will show that. And always you can also write some script around it. I mean, we have done some problem like that where it does print out like a report for your simulation. But if you have any specific need, we'll have to understand that. And of course, it can be customized depending on what most of the outputs are available. So you can customize a quality report based on that.
Okay, great, thank you. So the next question is, do you simulate the moving heat source, or is the simulation based on inherent strain? So the answer is actually both. So the current solution is a full thermomechanical solution, which means that we are accounting for the moving heat source to compute the thermal distribution, and then we use that thermal distribution to drive the stress analysis. So I mentioned, the mesh intersection toolkit, where we can take, an entire tool path. So we can take an entire laser path, and then we can, the solver figures out what the equivalent heat flux from that moving heat source is on each element for each time increment and applies that as a heat loading. So we do simulate the moving heat source. The inherent, so what I showed is, the full thermomechanical solution. The inherent strain method, which is what a lot of our competitors use, is typically faster, but may miss certain types of distortion. So things like buckling, it's hard for the inherent strain method to capture. So our full thermomechanical solution does capture things like buckling. But we understand that the inherent strain method is also important in the industry because it is faster. So we have developed an inherent strain method as well, which we actually call the eigenstrain method. And that is what we will talk about in this e-seminar in May. So this new eigenstrain method that we're coming out with, which is inherent strains. So the next question is our company has multiple locations. Does cloud allow us to collaborate on AMR across our offices? Yeah, that's correct. So for the cloud usage, it's very minimal local installations. The data is all stored on the cloud, so it can be used basically anywhere by anyone in any geo. So that definitely does allow you to collaborate across different AM offices. Okay, so then the next question is, as you know, it's not possible to simulate moving heat source on a full-scale model. So so the way we account for that is, so we do have the full scale model, but depending on what your time incrementation is, it really lumps your effects of your heat source. So we are accounting for the fact that the laser is moving at whatever speed across across the layers in a certain pattern, but we're going to lump that effect. So we are basically summing, okay, if we pick like a big time increment, so over 1 second or 10 seconds or something like that, all of the input from the laser in that 10 seconds gets lumped into a heat flux load that is applied over that time increment, which is how we handle accounting for all the details of the moving heat source, but we do that on a full-scale model with reasonable kind of simulation times. So I hope that makes sense. If not, we can have a further discussion about that. Do you extract thermal cycles? I think this means if we can extract the thermal data, like the temperature distributions that are resulting, and that is part of the results that we obtain from the thermal analysis. Can you show how the framework looks like, such as the starting software interface? I don't think we have time to show that, but yeah, maybe in a follow-up we can take a look at that.
Yeah, so maybe we'll take a note about that, and,
okay.
and you can drop us an email as well. So we'll try to have a like online session and show you the interface.
Yeah, that makes sense for follow-up.
Yeah.
And then I think this next question is for you guys. Does VS provide any services around AM? What are some examples of projects that VS can do?
Yeah, so we do provide, as we were talking about, so apart from softwares, we do consulting and training as well. So we do provide additive manufacturing services, and some of the projects, I mean, we recently have done one project where is basically to optimize the build performance and the process before you actually make the physical build. So we have run a couple of scenarios and tweaked the like basically speed of the laser beam and all to make sure there are certain requirements about the tolerance because of the distorted shape. So we wanted to minimize those tolerance, and we have simulated the building environment before they actually produce the material.
Okay, that's all the questions in the chat panel.
And in general, if you have any question, please feel free to contact us. We'll try to answer it, and of course we'll talk with the SOLID experts as well. And it's an evolving software. I think I mean I'm trying to be a little bit independent here, so I have for a long time using Simulia solutions, and because of their presence for nonlinear problem, and their solver is very good for that. I think the solution that Distortion has is very optimal right now, but of course, as the whole industry is moving towards the better manufacturing process, and a lot of new information and I mean new discoveries are being made, so the software is keeping pace with that. So it's very important for all of you to maybe attend the May 17th presentation as well, where they will talk about some of the new features that you might find more interesting or more aligned to your requirements. Yeah, and let me, we'll actually send our contact information as well, so you will have our email, phone number, and our website, and we are also on LinkedIn. So please feel free to follow us on LinkedIn, and we do post regular blog posts and articles on LinkedIn to keep our interested customers updated on any development. So, and we'll share those information in a way.
Okay, are there any more questions? Okay, I think we're good on the questions. Thank you again, Rachel, for the great presentation. Thank you, everybody, for joining us today. We will be sending out a recording of this webinar shortly. Thank you, everybody, and have a great day.
Thank you.
Thank you.
Thank you, Richard.